Hello, students. Hello, can you hear me? Okay. We have already started topic chemical bonding, and today we'll continue with it. See, today we are going to see valence bond theory. Okay. Last time we have seen VSEPR theory, and in order to explain the covalent bonding, scientists Hitler and London developed this theory, which is known as valence bond theory. This theory, it was further extended by Pauling and Slater. See the postulates of valence bond theory. When the covalent bond is formed, at that time, the half-filled valency orbitals of one atom overlap with the half-filled valence orbital of the another atom. Means for the formation of covalent bond, you need two half-filled orbitals, and the two electrons in the half-filled valence orbitals must have opposite spins. Means the first required thing to form covalent bond is that atom should contain half-filled valence orbital, and the another important thing required, that is these half-filled orbitals, they should have electron with opposite spin. During the bond formation, these half-filled orbitals overlaps and opposite spins of the electron get neutralized. Means those opposite spins, they get neutralized due to the overlapping and due to the pairing of these opposite spin electrons. This lowering of energy means, during the bond formation, the half-filled orbitals overlap and opposite spins get neutralized, and this greater the extent of overlap, stronger is the bond form. However, the complete overlap of orbital doesn't take place due to the internuclear repulsions. Means more the overlapping, stronger is the bond, and overlap means, however, this complete overlap of the orbital does not take place. Means it never possible that complete orbitals are overlap, and it is due to the internuclear repulsion. See the next point of the valence bond theory. These postulates of valence bond theory are asked for your exam. If the atom possesses more than one unpaired electron, then it can form more than one bond. So, number of the unpaired electron decides the number of capacity of an atom to form the bond. More the number of unpaired electron, more bonds will be formed. Means the factor which decides the capacity of an atom to form bond is nothing but the number of unpaired electrons. The distance at which the attractive and repulsive forces balance each other is that equilibrium distance between the nuclei of the bonded atom. And this distance means, at this distance, the total energy of the bonded atom is minimum and stability is maximum. The electrons which are paired in the valence shell, they cannot participate in bonding. Means for the formation of bond, unpaired electron is required. However, in an atom, if there is one or more vacant orbital present, then these electrons can be unpaired, or they are forced to form the bond by unpairing those paired electrons, and they can participate in the formation of bond, provided that the energy of these electrons must be similar, or means they differs from each other slightly. During the bond formation, the s orbital is spherical and it can overlap in any direction as it is spherical. But In case of the p orbital, which is having directional character, that it can overlap in the x, y, or z directions. Thus, the covalent bond is directional in nature. See, the interacting forces during the covalent bond formation. By now we have seen the postulates of valence bond theory, and you must have understood those. So the covalent bond is formed by the overlapping of the two half-filled atomic orbitals, and bonded atoms are stable than the free atoms, and the energy of the bonded atom is less than that of the free atom. So lowering of energy takes place during the formation of bond. This happens due to the interacting forces which develop between the nuclei of two atoms and also their electrons. These forces may be attractive and repulsive between the nuclei of A and electron of the B, and those arising from the attraction between the nuclei of atom A and electrons of atom B, and the repulsion between the electrons. The balance between the attractive and repulsive forces decide whether the bond will be formed or not. If the force of attraction is more, bond will be formed, and if the repulsive forces are more stronger, then bond will not be formed. We'll continue the same. See, page number 65, you can refer from your textbook. When the attractive forces are stronger than the repulsive forces, then overlapping takes place between the two half-filled atomic orbitals, and bond, means that is the covalent bond, is formed. This lowering of the energy during the bond formation, that is depicted in the potential energy diagram. So we'll see now this diagram. See, this diagram is showing formation of hydrogen molecule, which takes place between the two hydrogen atoms, each containing one unpaired electron. See, when hydrogen atom hydrogen atom with single unpaired electron come in contact with the another hydrogen atom which is also having single electron, and those electrons are having opposite spins. When they come, means when they are far away from each other, there is no force of attraction and no force of repulsion. So in that case, there is no bond formation. But if those atoms, means if these atoms are far away, there is no interaction and no bond formation. But when those atoms come close to each other, there is force of attraction due to the opposite spins, and overlapping between those atoms takes place, overlapping between the atomic orbital takes place, and bond is formed. When the repulsive forces are stabilized, the system means the system with the increased energy of the system, while the attractive forces decrease the energy of the system. Experimentally, it has been found that during the formation of hydrogen molecule, the magnitude of newly developed attractive forces contribute more than the newly developed repulsive forces, and as a result of this, the potential energy of the system begins to decrease, and when those atoms come close to each other, bond formation takes place. See, means we have discussed this diagram, and in this, means when distance is more less, at that time overlapping takes place. Overlapping between the atomic orbital, it is of different types. Formation of bond, it is nothing but the overlapping of the atomic orbitals having half-filled electrons with opposite spins, and in this orbitals holding the electrons vary in shape and energy and their symmetry also. So the extent of overlap, it depends on the shape and size of the atomic orbitals. On the basis of the above consideration, we have two types of bonds. First is the sigma bond and another is the pi bond. So sigma bond, what we'll see what is meant by sigma bond. See, when the overlapping atomic orbitals, when they overlap along their internuclear axis. Note this important point. Sigma bond is nothing but the overlapping of the atomic orbitals along the internuclear axis. And that type of bond formed due to the overlapping of the atomic orbitals along the internuclear axis is called as the sigma bond. And this overlapping may be between the two s orbitals or between one s and two p orbital or the two p orbitals. See, the first type we'll see formation of the sigma bond by overlapping of the two s orbitals, and you can take example of hydrogen atom in this case. So this is one s orbital of one hydrogen atom, and this is the another s orbital of the another hydrogen atom. Each hydrogen is containing one s1 electron, and this is having single electron and its spin is clockwise, and another hydrogen atom which one s orbital is having anti-clockwise spin. And when they overlap along their internuclear axis, see, these are the nuclei of the two hydrogen atoms, and they are overlapping along their internuclear axis, and formation of the hydrogen bond, that is hydrogen covalent bond, takes place by overlapping of the atomic orbitals to 1s orbitals along their internuclear axis. And see, this hydrogen bond is formed, or hydrogen H2 molecule is formed. Now we'll proceed towards the next, that is a formation of sigma bond by overlapping of the p orbitals. See, in this type of overlapping, as this p orbital is having directional character, this p orbital from the different atoms, see, this is the p orbital of one atom. For example, this is a p orbital of one fluorine atom, and this is p orbital of the another fluorine atom. You know, fluorine, it is having electronic configuration 1s2, 2s2, 2px2, 2py2, and 2pz1. You know, fluorine is having atomic number 9. So this is the electronic configuration 1s2, 2s2, 2px2, 2py2, and 2pz1. Means it is having single unpaired electron in the 2pz orbital, and this is 2pz orbital of one fluorine atom, and this is the another 2pz orbital of the another another fluorine atom. When these 2pz orbitals of the two different fluorine atoms overlaps along their internuclear axis, then sigma bond is formed between the two fluorine atoms and fluorine molecule is formed. See, this is the overlapping of the two pz orbitals of the two fluorine atoms along their internuclear axis. This is the internuclear axis. Now we'll see the another type of overlapping, and that is sp overlapping for the formation of the sigma bond. And example you can consider, that is formation of HF. See, in this type of overlap, one s orbital which is half filled, for example, it can be of the hydrogen atom, and this is 2pz orbital of fluorine. So this is the formation of HF covalent bond, that is sigma bond. And this overlapping between s orbital and p orbital, it is along the internuclear axis. See, electronic configuration of hydrogen is 1s1, and fluorine, that is 1s2, 2s2, 2px2, 2pyz, 2pyz, then 2pz1, 2py2, and 2pz1. This is the one unpaired electron present in case of the hydrogen, and this is single unpaired electron present in case of the fluorine. So when this hydrogen overlaps with fluorine, it forms HF covalent bond and HF molecule. This is the sigma bond formation in case of the HF molecule. And this was all about the formation of the sigma bond. Now we'll see how pi bond is formed. So up to now, you must have understood that sigma bond is formed by the overlapping of the two half-filled atomic orbitals along their internuclear axis. And pi bond means what is difference between the sigma bond and pi bond? You will come to know now. When two half-filled orbitals of the two atoms along their sideways, or you can say laterally, when this side of the p orbital overlaps with the another p orbital along its side. This is in the lateral overlapping, and or you can say sideways overlapping, and this is the formation of the pi bond. Means sigma bond is formed by the overlapping of atomic orbitals along their internuclear axis, while pi bond is formed by the overlapping of the atomic orbitals along their side, or you can say this is the lateral overlapping, and it results in the formation of the pi bond. But when you see or when you study this valence bond theory, it explains well the formation of the covalent bond in case of the simple molecules like H2, F2, HF, etc. While the maximum number of the covalent bond which an atom can form, that is dependent on the number of the unpaired electron present in the valency shell of that atom. But in some cases, the number of unpaired electron is not matching, or you can say that cannot be explained. The formation of some molecules cannot be explained with the help of that valence bond theory. And so this new concept of hybridization was introduced later on. We'll see what is meant by hybridization. See, the molecule formation of BF3, boron trifluoride, or formation of the molecule of CH4, methane, or formation of carbon tetrachloride. These formations, those cannot be explained with the help of just valence bond theory. But some new concept is required to explain this, and that is the concept of hybridization. Hybridization was put forth to explain the formation of such complicated molecule BeH2, BF3, CH4, CCl4, etc. So we'll see one by one how this formation of BF3, CH4 can be explained. See, beryllium, it is having electronic configuration 1s2, 2s2, and it is not containing any unpaired electron in the ground state. So how can it be possible to form this molecule BeH2? That is explained on the basis of the hybridization concept, or the formation of BF3. Because in case of boron, see the electronic configuration 1s2, 2s2, and 2p1. So there is only one unpaired electron in case of the boron. So BF3, that is the this boron is forming 3 bonds with 3 fluorine atoms. But here only one unpaired electron is present, so it can form only one bond. But it has formed 3 bonds. So this formation of BF3, that is also explained on the basis of hybridization. So we'll see what is that concept of hybridization. This was suggested that one electron in 2s orbital of this beryllium, it has been promoted to the vacant 2p orbital. See, the electronic configuration in ground state of beryllium is 1s2 and 2s2. And in the excited state, this beryllium, means one of the electron from this 2s, see this is the 2s orbital, it has been promoted to the vacant 2p orbital, and now there are two unpaired electrons present in beryllium. So it can form now two bonds, and this is called as hybridization. So now we'll see definition for hybridization. Hybridization, it is nothing but the mixing of the valency orbitals of the same atom and recasting them into the equal number of the new equivalent orbitals. That is called as the hybrid orbitals. See, this is mixing of the two atomic orbitals and recasting. These two atomic orbitals are of the same atom, beryllium atom. It is means this 2s and 2p, both atomic orbitals are of the same atom, that is beryllium. One of the electron from 2s is promoted to 2p, and now there are two available unpaired electrons for the formation of the two bonds with hydrogen, that is the formation of BeH2. Same in case of the boron. See, boron, in case of boron, there is single unpaired, there is no unpaired electron in case of the boron in ground state in 2s orbital. And here only one unpaired electron is present in the 2p orbital. But in excited state, one of the 2s electron is promoted to 2p. Now there are 3 unpaired electron present in the valency orbital of this boron. So it can form now 3 bonds, and this mixing and recasting of the atomic orbitals of the same atom having slight difference in their energy, that is called as the hybridization. This is the concept of hybridization, mixing and recasting of the atomic orbitals of the same atom having slight difference in their energy, or their energies are almost same. See, in case of the carbon, it is having electronic configuration 1s2, 2s2, 2px1 and 2py1. So there are two unpaired electrons, but when this molecule carbon tetrachloride CH4 or methane or carbon tetrachloride is formed, there is formation of 4 bonds. So how is that possible? That is explained on the basis of the concept of hybridization again. See, the one of the electron in 2s orbital, that is unpaired or promoted to the empty or vacant 2pz orbital, and now there are 4 electrons, 4 unpaired electrons are present in case of the carbon, and those electrons are available now for the formation of the 4 bonds to form either CCl4 or CH4 bonds. So this is the concept of hybridization. I will revise once again the definition for hybridization. Hybridization is, you can underline that in your textbook also. Hybridization, it is nothing but the mixing and recasting of the atomic orbitals of the same atom to form the number of bonds. Then we'll see the steps involved in the hybridization. The first step involved in hybridization is the formation of the excited state, and another is mixing and recasting of the atomic orbitals. See, the formation of the excited state. Again, example of beryllium difluoride is considered. In case of the beryllium, one of the electron from the 2s is promoted to 2p, and now there are 2 unpaired electrons present for the formation of the 2 bonds with the 2 fluorine atom. and this is the mixing, or this is formation of the excited state. Now mixing and recasting. In this step, the two s and p orbitals, see this is s orbital and this is p orbital, there is slight difference in the energies of the 2s and 2p. They mix with each other and redistribution of the electron takes place. Electron density is redistributed and energy is also redistributed, and two new orbitals having exactly same shape and energy is formed. These new orbitals arrange themselves in space in such a way that there is minimum repulsion and maximum separation between them. So during the formation of sp hybrid orbitals, as in case of the beryllium, the two sp hybrid orbitals are at the bond angle 180 degree. Then we'll see what are the conditions required for the hybridization. See, the first condition required is orbitals which undergo hybridization, they should belong to the same atom, as in case of the beryllium. See, these atomic orbitals belongs to the same atom, that is beryllium. So that is the first and most important condition for the hybridization, that the atomic orbitals which undergo hybridization should belong to the same atom. Then another condition, orbitals having nearly same energy can undergo hybridization. So 2s and 2p orbitals undergo hybridization, but 3s and 2p orbitals cannot undergo hybridization because their energies are not same or not equivalent. So the another important condition for the hybridization is that the atomic orbitals which undergo hybridization must have equivalent energy or slight, very less difference in their energies. They should have nearly same energy. Then we'll see the characteristic features of hybrid orbitals. See, the first important characteristic feature is the number of hybrid orbitals formed is exactly same as the participating atomic orbitals. You can see the example. See, number of hybrid orbitals are 2 and participating orbitals are also 2. 1s means this 2s and 2p. 2 atomic orbitals are participating, so number of hybrid orbitals is also 2. Then they have same energy and shape. The means atomic orbitals have same energy and shape. Hybrid orbitals are oriented in space in such a way to minimize the repulsion, and they're directional in nature. They are directional in nature. The hybrid orbitals are different in shape from the participating atomic orbitals, but they bear the characteristic of the atomic orbitals from which they are derived. Each hybrid orbital can hold 2 electrons with opposite spins. And the next feature is hybrid orbital has 2 lobes on the 2 sides of the nucleons, and one lobe is large and another is small. Covalent bond formed by hybrid orbitals are stronger than those formed by the pure orbitals, because the hybrid orbital has electron density concentrated on the side with a large lobe and the other is small, allowing great overlap of the orbitals. And today we have seen up to this part, and rest of the part of this topic will continue in the next lecture. Hope you have understood this. Bye, students.